Okay, welcome to second lecture in this series of lectures on introducing Fukaya categories. So today we are going to talk about Morse homology and floor theory, and in between the two, of course, I need to give you a brief primer on symplectic manifolds or symplectic geometry, just a little bit, so that this kind of makes sense. We have a footing where we can stand and we can talk about floor theory. Okay. All right, so I have some references for you. So some general references on manifolds. Is an excellent book. It's called Introduction to Manifolds by Loring 2. It's very, very reader friendly, and it also gives you an introduction to homology theory in terms of Durham homology. And if you're looking for a nice, first exposure, or maybe not your first exposure, but nice exposure to homology theory or Durham cohomology, then this is the book to look at, and also for in general calculus on manifolds. Okay, and then for symplectic stuff, I recommend these lectures on symplectic geometry by Ana Canas da Silva, and also Introduction to Symplectic Manifolds by Dusa McDuff and Dietmar Solomon. These are both excellent books. Both are to some extent reader friendly, and with their especially the lecture notes are a good starting point. And then for Morse theory, the standard, of course, I haven't mentioned Milner's book. That's probably blasphemous not to mention that, but of course here is Milner's book, which is this classical treatment of Morse theory that I forgot to add. And then you can also use, for the classical approach, an introduction to Morse theory. That's probably the title, but it's by Matsumoto. And the book that we'll be following is Morse theory and floor homology. So this is the treatment that we need to follow, because we want to go towards floor homology, towards the definition, via Morse theory, okay? Or with using this approach of Morse theory or Morse homology, whatever. Okay, so we can look at the references again. So now we start with, because I want to eventually start telling you, I want to start with Morse theory and eventually tell you what Morse homology is. And before I can do that, I need to tell you maybe very quickly in a few minutes something about homology. So homology is an invariant that you associate to a topological space. So we've seen the homology functor already yesterday. So you start with the category of topological spaces, and you go to a category which is could be the category of a billion groups, of vector spaces, of modules, whatever, but here you have something that's associated to a topological space. So they come in a variety of flavors, and of course there are theorems that establish a connection between different flavors, which means that if you for a given topological space, if you find a different homology, I don't know, blah blah, or different cohomology and a different flavor, then they would all be isomorphic to each other, because it's an invariant of this space. Okay, so whatever variant or flavor you're following, they all start with what? They start with a complex, a chain complex. So a chain complex is, again, it's a sequence of, could be a sequence of a billion groups, could be a sequence of k vector spaces, could be a sequence of R modules, etc. Okay, so if you're working the category of, let's say, vector spaces, then you have, these are vector spaces, these are components, they represent I-dimensional objects, or you can say I-dimensional information about your space that you started out with, and these are the differential maps or maps which send I-dimensional objects or features or information to I minus one dimension down features, objects, or information. And the fact that this D is a differential, or that this pair is a differential complex, comes down to showing that the differential squares to this map squares to 0. Okay. And that's what defines this to be a chain complex. Anyway, so what's the homology? Homology then is this quotient. So this means that you're able to make this quotient. So this implies that the image of d, here you have di plus 1, the image of di plus 1 in Ci is a subgroup or a subspace of the kernel in Ci. So you have a kernel here and you have an image here, and you can take the quotient. So this guarantees that it's meaningful to take the quotient, and when you take this quotient, you get the homology. Okay, so this is called a certain homology, whichever flavor you're talking about of the topological space we started out with. So you can dualize this construction. What does that mean? So for simplicity, let's just assume that we're taking linear maps between vector spaces, let's say real vector spaces, and that's collectively, I also mentioned yesterday, is what you would call a graded vector space. Okay, so it's a sequence just like this, but now I'm going to dualize the sequence. What does that mean? That means that I'm going to consider C with an upper index, which is basically you take all the homes or functionals on that vector space. So that's the definition of a dual vector space. And so as you can see, the relationship between lower I and upper I is that one is the dual of the other. Okay, and when you dualize, what happens to these maps is that the arrows get reversed. Okay, so now you'll have C upper dot D upper dot, which is the dualized complex. It's going to be something like this. So let me write it in the same manner, the way it's written before, blah blah, and now you'll have D0, D1, and etc. Okay, so now your differential, sorry, I need to put an upper index here. Okay, so this is just the adjoint of that linear map that you had in the beginning. Okay, and so you have this construction, and similarly this is a complex that boils down to showing just a minute. Okay, that boils down to showing that these square to 0. So it's di composed with di minus 1 is 0. Okay, that means you can form that quotient. So now you'll have hi of C upper D upper dot, and this is the kernel of di modulo. So you'll have at I, you'll have di, the kernel of di and the image of di minus 1. Okay, that's what it looks like. Okay, so the bottom line is that you start with a complex, some suitable complex, and you arrive at the corresponding homology of the space that you started out with. Okay, that's the moral of the story here. Yeah, if there are any questions at the end, I could say something about really what this encodes, what kind of information, and maybe give you more references if you're interested. But maybe it's good to move on to. So maybe I can give you examples. So for example, so simplicial homology. So you have, in this case, each Ci is, let's say, generated by I-dimensional simplices. I won't give you the definition, but this very roughly means that C0 would be generated by vertices, those are zero-dimensional simplices. C1 would be generated by edges, those are one-dimensional simplices, and C2 would be generated by two-dimensional simplices, which are triangles, and so on. Okay, and when you look at the boundary map or this differential, it maps, let's say, a an edge to a difference of their vertices, of its boundary points, which are the vertices of that edge. Okay, so anyway, so homology, simplicial homology would count cycles and would mod out the boundaries, cycles that are also boundaries. Okay, so you look at cycles, it basically counts the cycles that are not boundaries. Okay, so that's the cycle is basically what you call in layman terminology holes, and so that's one example. Second example is of Durham cohomology. So here again you start with a suitable complex. The complex is given by so this is an upper index because we're talking about cohomology here. So this is generated by I forms on the manifold, and whichever manifold you're considering. And yeah, so the homology is going to give you an isomorphism, so there's a Durham. So, but before that I need to tell you what the di is. So the di goes from so the di goes from I to omega I plus 1. So it raises the degree by 1, and this is just the exterior derivative of forms. So if you start with functions, the zero forms are functions. You take the exterior derivative, you get a 1 form. Okay, start with an f, you go to df, and you start with a df or something that's a 1 form. You take the exterior derivative, you get a 2 form, and so on. Okay, so that's the exterior derivative. So the Durham theorem or Durham map maps every, let's say, I form to this home of, so these are singular cochains, singular chains. So that's a complex which is formed by singular chains. Instead of simplicial chains, you look at singular chains. So they're a close cousin of generalization, a close cousin of simplicial homology, or chains in simplicial homology. So you look at these and you dualize this, and that's where you get the okay, so what is this? These are functionals on this vector space. So you have, let's say, an I form alpha. This is mapped to this functional, which maps a chain to this integral of this form over sigma. Okay, and so the Durham theorem says that this induces an isomorphism in homology or cohomology, because you've dualized the homological sequence here, and here you already have a complex which is with an upper index, and so you have an isomorphism in cohomology, and that's an instance of what I was talking about, that they're isomorphic. You have 8 star Durham of M. Let's say M was our manifold, is isomorphic to 8 star M of R. So this one here is what you call singular cohomology of M. Okay. All right. So what do we want to do? We want to do Morse theory. In fact, talk about about Morse homology. So let's start with Morse theory. That's maybe the second section for today. So that was just a quick overview that did not do justice to homology theory, but anyways, maybe we will see these things, the theme repeat, so it should be, I guess, should be okay. Okay, so that's the pipeline. You start with a compact manifold, and so Marx and Morse in the 20s discovered that you could actually associate to a complex, to a compact manifold, a Morse complex. So what's a complex? It's a usual sequence of vector spaces, modules, a billion groups in this case, and maps between them. Okay, and this gives you an invariant of M, which is called Morse homology. Okay, so this is as an application, you know, this helps you distinguish between it's an invariant of the space, which means that if you have two spaces that are the same, then their Morse homology would also be isomorphic. Okay, so it helps you distinguish between spaces in the sense that if the Morse homology of two spaces is different, then the spaces cannot be the same. Okay, and of course there are other applications like Brouwer's fixed point theorem or the Hairy-Ball theorem and stuff like that. Okay, so let's see. So what is the Morse complex and how do we get Morse homology from that? Okay, so the general idea is that you start, so now I'm talking about this thing here. You start with f, that's a Morse function. Okay, whatever that means. And from here you go to this complex, which is spanned, so each Ci is spanned by critical points of f. We'll recall what this means. And then, of course, you need to define, so a complex has two pieces of information. You need these spaces, and you need, of course, you need these graded pieces in each homological degree, and you need maps between them. So what are the maps? The maps are differentials, so you need to define differentials, some meaningful definition for this. And then, of course, so this is the tricky bit. This involves 3 steps, which are called transversality, compactness, and boundary. So transversality, so that a certain manifold space that comes about as a result of going from here till here is going to be a manifold and of the right dimension, and so you can count. So compactness is required, so you're able to count something, and boundary is again, so everything fits together nicely. We'll talk about this a lot, so you don't have to worry so far. Okay. All right. So let's start with whatever our initial data should be. So again, we start with initial data. I need to first of all define what these are, and then we move on to defining the differential. And once you have a complex, so you see in these two steps we've achieved a complex. And you have a complex, you just go to pass to homology and you get Morse homology. Okay. So what's the data? The initial data is the following. You have a smooth, let's say closed compact manifold M of dimension n. Okay. And 2, you have a function f on M to work with. So this M could be maybe this could possibly be with boundaries, so maybe I'll just make it smooth and compact. And you need a function on M to work with. So the first definition has many parts. So a point on M is called a critical point if, let's say, of F, if of course when you look at a function on manifold of dimension n, there's a way to linearize this function and pass to, using a chart, pass to a map from M to R, because it's a manifold of dimension n, from this function to something which is from Rn to R. Okay, so that means in a certain chart, which is around a patch on the manifold around this point, you can actually think of this function as a function from Rn to R. And what that means is that now you're looking at a function of several variables, a real valued function of several variables. And so for it to be a critical point, you need vanishing of all partial derivatives. Okay, so that means that the differential of f at p vanishes. Okay. 2, the Hessian of f at p, which is, well, it's defined to be the transpose, the Jacobian of the gradient of f, which is kind of complicated, but you can also understand it in terms of bilinear form on the tangent space of M at P. But so let's just write down the matrix, which in a chart around P, or local coordinates around P, can be written as the matrix of second or mixed partial derivatives of, so I and j go from 1 to n. Okay, that's the matrix. All right, and that's the Hessian of f at p. Okay, and now we can go to the second, another definition. So P, let's call this 3, P in the set of critical points of F. So this is the set of critical points. So this is where f has all of its partial, all points where f has all of its partial derivatives vanishing. So P is in the set of critical points is called non-degenerate if the Hessian at P of F is non-degenerate. And what does that mean? That just means that it's a matrix, right? So this thing here has is non-singular as a matrix. Okay, that's what this means for this to be non-degenerate. Okay, and then let's say number 4. Morph is a function on M is called Morse. So now you know what a Morse function is. If all of its critical points are non-degenerate. Okay. Okay. So now another part of this definition is to define the index of a critical point. So let me give it a heading, index of a critical point. So we denote this by index of P. But what is it? So if n minus I is the signature of the Hessian, at P, we call I the index. So that is this I of P is this small I. Okay. So you can right. So the determinant of the Hessian evaluated at a point gives you the Gaussian curvature of the function at that point. And so if, for instance, your Hessian matrix has all real eigenvalues, then you can interpret this in terms of the signs of the eigenvalues of the Hessian matrix. Okay, so I'll say what that means in a minute. So before that, let me just give you an example. So the example is of the height function. So you have this sphere and f is the height function. What does that mean? You just take this f from S2 to R and you just map, so the level sets for each point in R are these circles on the sphere. Okay, so at this level, at this height, you have all these points being mapped here and so on. So that's just the height function of your manifold. So if you want a formula, we can write it as f x y z, considering this is a subset of R3 as just on whichever height this point lies. Okay. So this is a Morse function with, and you know exactly how to check it. You look at the Hessian, whether it's non-singular at each of the critical. So the first thing you need to do is find out the critical points. So what are the critical points? You look at this and instantly you see that it has two critical points, the north pole and the south pole. So with critical points, the north pole and the south pole. And now I want to see what is the index of n and what's the index of s. Okay, so we see that in this case, you see around n, you see negative curvature, and this is so if you can interpret this in general, if your matrix has real eigenvalues, then you can interpret this as all negative eigenvalues. So this means that your n is 2, so n is equal to 2, that's the dimension of your manifold, that's the n over here. So you have all negative. This means that this, right, so you have, this means that this thing is, what do I want to say? Yeah, I want to say that this means that this thing is 0, that's the positive part, that's the negative part. So that means that this thing becomes 0, so I is equal to n, which is 2. And so you have with index 2 for n, and likewise this is of positive curvature, and this is equivalent to saying that here you have I equals 0, so no negative eigenvalues, and this is of index 0, okay, respectively. Okay. So now that we know what the critical points are of a function, and we know that for a Morse function, we want them to be non-degenerate, all of them. And we also know how to attach or to assign an index to a critical point, okay? That's important. So now I can imagine, or we can imagine, what the complex should look like. So you have, because it comes out of a function, we are talking about each component Ci being generated by critical points, okay? And what's the degree, what's the I? The I is going to be exactly the index of those critical points generating that Ci. So I'm going to write that down here. Maybe I can keep that side on that, these steps on the board for the moment, and write down so the Morse complex is defined as the graded module. So what does that mean? We're looking at modules for each component. We're looking at modules, like in the case of Durham, we were looking at vector spaces and so on. So you have a graded module, C dot, where each Ci, where the dot is equal to I, of f. So this is because it depends on the f, so we write this dependence on f, is defined to be generated over Z mod 2 by critical points of f. So let me just write this down in the next line so it's easier to read. So the Ci is the Z mod 2 generated over Z mod 2 by critical points of f, such that the index of this P is exactly that I. Okay, so C0 would be generated by critical points of index 0, C1 would be generated by critical points of index 1, C2 would be generated by critical points of index 2 if there are any, and so on and so forth. So, for this example of this sphere, so continuing with that example, we have Ci of f equals z mod 2, z mod 2 and 0 otherwise. So, it is generated by index 0 by the south pole, this point which is a critical point, and at index 2 it's generated by the north pole, and that's all. We don't have more critical points, so we don't have any more other components. Okay, so that's all we have. All right, so let's just write it down like a sequence. So this gives, you have C0 of f going to, sorry, the other is C2 of f, C1 of f going to C0 of f, yeah, and there is nothing in the negative degree, so I can take this to 0, and of course there is nothing here either, because for all other indices, for all I different from 0, 2, you just have 0. Okay, so there's no C3 of f, there's no C4 of f, and so on. Okay, so what is C1 of f? Because 1 also belongs here, it's not equal to neither 0 nor 2. So this is 0, that's just the 0 module. And here you have something that's generated by n, and here you have something that's generated by s. Yeah. So now, when you look at this complex, I don't even need to define a differential for this particular example, because you have something that goes to 0, and the only way you can go to 0 is, the 0 map, and here you have 0 being mapped here. So again, you have the differential, whatever, however fancy they may be in a general case, they are just trivial in this case. Okay, so here instantly, without any further work, we can just find out or compute the homology, in this case, which would be called Morse homology of S2, because it comes out of the Morse complex. Okay. All right. So this means that let's say hi of, let's say, C dot f is, so the kernel of this map is everything over here, and everything else is 0, so the image is 0. So you have this thing generated by n, so that's just a copy of z mod 2 when I is equal to 2. And you have a copy of z mod 2, if you like you can write the class of n next to it, but in fact it's just a copy of z mod 2 and a z mod 2 for I equals 0. How did I get that? The kernel here, is everything, and the image under the 0 map is just 0. So you quotient by 0, you just get everything, which is what I have here, and 0 otherwise. Okay, and if you're familiar with the singular homology or the simplicial homology, or whichever homology of the sphere, this is consistent with that. Okay. All right. So, but we need to learn how to do this in general. So we don't know that yet, and it's a long procedure to do that in general. So that's what I'm going to try and do now. Okay. So I just want to make a quick remark. So So over here, which I forgot to say, so the eigenvalues of the Hessian at this point. So I told you that the determinant of the Hessian at a point gives you the Gaussian curvature of the function at that point. Yeah, but so so the eigenvalues of the Hessian, they give you principal curvatures of the function, and the eigenvectors are basically the tangent directions. You see, here you have a tangent space that's two-dimensional, and you have tangent directions on this, which basically give you directions to move along on the manifold. So this is just locally approximating the manifold at this point, this tangent plane that I've drawn around at the North Pole. So you get the eigenvectors are basically principal directions. So the vectors that live in here, but they give you directions to move on the sphere. Okay, and so we're looking for ones where the function is decreasing. You see, you look at the height function, the function is decreasing in this direction along the ball. Okay, which is why the index is I and not n minus I. Okay, you look for the negative directions, where principal curvatures, the directions where the function is decreasing. Okay, so that's something important that I forgot to mention initially. Okay, so now that we have the Morse function, we have an example. There are questions whether Morse functions exist always. So there is good news that you can always approximate any function by a sequence of Morse functions. So if you like, you could say that a certain kind of functions, very simple to express, they are Morse, and that the set of these functions at any point is open and dense in the differentiable functions on the space of differential functions on a manifold. Okay, so the first thing I wanted to say is that any function can be approached by a sequence of Morse functions. So locally in a Morse chart. So what do I mean by a Morse chart? I just mean the chart around the point on the manifold, a local patch on the manifold around a point where the function is, which is critical point for the function, and the function is Morse, which means that the critical point is a non-degenerate critical point. That's what I mean by a Morse chart. Okay, so you can express the function in a certain way, and so locally you can express f by just mapping through the chart to Rn. You can express it as f of p minus xj squared. So this is j going from 1 to I. So the I is again the index of the point, and plus xj squared I plus 1 going to n. Okay, so this doesn't mean much, but what I want to say is as a consequence of this, the critical points are isolated of a Morse function. Okay, so what does that mean? This means in particular that the number of critical points of f is finite. Okay, what does that mean? That means that if you have a complex, the Morse complex, then the complex is finite. So it doesn't go on forever and ever. And moreover, for each component, you have finitely many critical points in every index. Okay. All right. So how do you define the differential? So for the differential of the Morse complex, so that's the slogan. This is defined counting by counting downward flow lines between critical points. Okay. So whenever you have a flow, whenever you have a vector field, you can define the flow of that vector field. So so you can think of the tangent vector field on a manifold, and so you can look at these tangent directions which point towards decreasing f, and that gives you downward flow lines. So and you integrate that vector field. That's how you say it in differential geometry, and you get these paths or trajectories, and that's what you want to count. Okay, and of course you don't want to count something that's infinitely many, because that's not going to help. So you want something to be, these things to be finite. Okay, so we'll see how we're going to achieve that. And in fact, these are the 3 steps that I was mentioning: transversality, compactness, and boundary, that helps us achieve the target. Okay. Okay. So let's see where we want to go from here. Okay, I need to give you a definition and some pictures, and then we can continue after the break. Okay. All right. So you see, I need to for these downward flow lines, I need some extra data. So the data required to be able to do this is you have a manifold, you have a Riemannian metric on G, so this on the manifold. So G is a Riemannian metric on M. So you can always construct this using, if you know what a partition of unity is. And so on something I want to write in brackets, on Morse charts, this coincides with the standard Euclidean metric. That's no surprise, because locally the manifold is like Rn. Okay. All right, and that's one thing. And next we need a vector field. So this is the gradient, like the gradient vector field, but in fact it points in the opposite direction. So the gradient vector field tracks the direction in which the function increases. Okay, but this we want to do it with the opposite sign, because we want to track where the function decreases. Okay, so this is x equals minus the gradient of f. So you just take the gradient and you just reverse signs. So this is called a pseudo gradient. Okay, so So this is the pseudo gradient is characterized by the following, that the differential of f at x of the pseudo gradient is always less than 0, okay, for all x or p belonging to the critical points. Oh, sorry, not the critical points. It's 0 for critical points outside the critical points, m minus critical points. Okay, so that just tells you the function is decreasing. Okay. All right, so I just want to draw some pictures, and then maybe I can draw them here. So this is already clear. We're going towards Morse homology once we define the differentials. Okay. So we have what is called the height function for the sphere for the torus, and let me draw that later on. So we've already discussed this has two critical points, and between these two critical points, this is how you draw the gradient flow lines, the pseudo gradient. Flow lines are the pseudo gradient. Okay, and so for the torus, we have these critical points. So I'm just drawing pictures for the moment. We're going to compute all these examples later on. So you have flow lines coming like this and so on. Okay, and then these are all mapped to R, the height function, all of them. And now I'm going to take the deformed sphere. Okay, so that's a deformed sphere. So topologically it's the same as the sphere S2. And here you see I've raised the number of critical points after this deformation to 4. Okay, and this is again considered with the height function. You get these trajectories, okay, and so on. All right, so there, well, in fact, there are lots of them, and blah blah. Okay, what's important is that they point downwards. And what does that mean? If you remember, this was, let me write down the index with blue. So you remember that this was a critical point with index 2, this was a critical point with index 0 on the sphere, okay? So these downward trajectories go from a higher index critical point to lower index critical point. They could go from, the jump between the index could be more than 1, like you see in this case, goes from an index 2 critical point to 0. Here you have a jump of 1 for this trajectory, here you have a jump of 2, and so on, okay? So again, it goes from a higher index to a lower index, and then to a lower index. So it either goes to the same index, okay, which is the case for this flow line, okay, or it goes to a different index, okay. And likewise, we see the same situation over here. So these pictures really just talk to you and they tell you that this is what's happening. We need to keep track of these trajectories and count them somehow. So don't forget this slogan, okay? We're going to count these somehow. Okay. So these are called Morse trajectories, okay? Let me write that down in green. These are called Morse trajectories, okay? Flow lines of the pseudo gradient, or sometimes people also call them negative flow lines, but this is maybe just me calling it imagining stuff, but I don't know. But this is for sure fine. Okay. All right. So I just need to make a quick definition, and then we can talk about these steps in like after the break, if that's okay. So let me just give you this definition. So let F. So I'm going to introduce some more terminology so we're able to, talk about, let's say, transversality. Okay, so F is a Morse function always. X is the pseudo gradient. You already know what the formula is for F. And now for any PQ that are critical points of the function, MPQ is defined as the set of all points lying on flow lines between P and Q. Okay, what does that mean? That means something like this picture, or abstractly you have a P here and you have a Q here, and you're looking for all of these trajectories, and maybe there's an intermediate point here and they come through that intermediate point, who knows, but this is what this entails. Okay, all right. And now, so you see over here there's no restriction on saying whether P and Q are of consecutive index or not. Okay, could be like they could have a jump of more than one. All right, next you have an LPQ. This is a quotient of PQ mod R. So what is this? So the claim is that R acts on this space of trajectories, flow lines, Morse trajectories, and it acts in the following way. So this means, maybe I should write it like this: R cross MPQ goes to MPQ, the usual way you write action. And so for any T and a point in this, you see these are points that lie on these flow lines. Okay, so it's the set of all these points, Okay, so you take a point on some flow line, and this gets mapped to the flow along that trajectory. So let's say you start from here and it gets mapped to this point over here, okay, along the same trajectory. That's the action. And so this quotient, what this quotient is going to do is that it's going to identify all these points with, let's put a yellow dot, one point on each trajectory. Okay, that's the quotient. So let me quickly write that down. So you get 1 point representative of all, for all points on each trajectory. Okay, so you have LPQ is, so the quotient contains one point representative of each flow line or Morse trajectory. Okay, that's the definition. All right, and so let's put in a quick remark. So what do you have for when P is equal to Q? So I suggest you look at this flow line over here, or maybe look at this one. It's between P and Q that are different. What if you have PP? That means you start at the point and you keep standing at the same point and you don't move. And when you don't move, that means that all you have is a single point. Yes? And the action of R on that single point is already trivial. Yeah? It just stays there. That point stays there. And so this is just that point. Okay? That's all you've got. All right. And if P is different from Q, this helps you visualize what this is. LPQ can be written as intersecting MPQ with a level set corresponding to alpha. Okay, let's see what that means. So this is what that means. So you look at this R and you take this alpha. So that's my P and that's my Q. They're two different critical points. And that's an alpha between f of P and f of Q. Okay, and you look at the slice. So let me take a different color. And you look at this slice corresponding to alpha. It's this level set. Okay, and for each trajectory, you just take that representative. Okay, that's your L. Okay. All right. So maybe we can stop here, take a break of 5 minutes, 6 minutes, and then we will come back to define these 3 steps of transversality, compactness, and boundary. Okay. Okay, so maybe we can resume from where we left. So I need to give you, so don't forget the slogan. We need to count these trajectories somehow. So at the moment, we have so I've told you the set of all flow lines and its quotient, and now I need to tell you something more which pertains to the local picture on a Morse chart, and I also have a picture to show you. So let phi t, so it's the same phi over here, denote the flow of the pseudo gradient. So it's going to flow points along these flow lines or Morse trajectories. Then Ws at P. So P is a critical point of F. And you can define this Ws of P. This is called the stable manifold of P. This is the set of all points. I choose not to write down the formula. All points in M lying on trajectories ending at P. Okay, so these are the flow lines that are coming into that point, the critical point. Okay, and we know something about this manifold, that this is diffeomorphic to R n minus the index of P. Okay, so if you have a critical point which is of index small I, then we're talking about R dimension m minus I. Okay, that's your stable manifold. And I'll show you in a second what this looks like in a local Morse picture. So these two pictures I've actually taken from, so I basically copied them from this book of Damian and Audin, and I told you that this book specifically targets floor theory, but starting from Morse. Okay, so if I can enlarge this a little bit so you can see it better. You see, that's your critical point, and if you're able to see this arrow that points downwards, so that's a trajectory that points downward and comes into the critical point. And this is a trajectory that points upwards and comes into the critical point. So this over here is what you see as the stable manifold, okay, around the critical point, and the stable manifold of M at P, a stable manifold of P. Okay, and so these are all trajectories that end in the critical point P. Okay, so over here you also see these flow lines of the Morse trajectories. Okay, this is just to show you, and of course this chart is split, or local coordinates in this chart are split in two parts, the ones that correspond to the negative eigenvalues and the ones that correspond to the positive or part. So maybe I should say the ones that correspond to the I coordinates and the others that correspond to n minus I. So this is a schematic picture. This is an n minus I axis, so it's of dimension n minus I, and this is an axis of dimension I. Okay, so here you have this diffeomorphism between the stable manifold and R to the power n minus I of P. Okay, and so that's the picture around local maxima or minima, and that's a picture around a saddle point. Okay, so again you see the stable manifold points that go, trajectories that go into this critical point. Okay, so let me show you this picture. So again you see these arrows coming into A, and this is what it looks like. You see, now you're looking at a Morse trajectory, and along this R you see from minus infinity 0 you're going into towards infinity, you're going into that critical point. Okay, and you combine all of these, you get this stable manifold, yes, which is homeomorphic, in fact diffeomorphic, to R n minus the index of P. Okay, and the boundary of this manifold is this sphere of dimension 1 less. Okay, so you have n minus I minus 1. Okay, so hopefully that makes some sense. And then similarly you could define the unstable manifold. So this is the ones that are leaving P. So that's what you see here. So you have this arrow pointing to the left, pointing out towards the right. So that's the unstable manifold. And when you look at this picture, you know instantly what I should be writing here in point D is that this is diffeomorphic to R, the complementary dimension, index of P. Okay. All right. So maybe we can have a quick look at. So the idea is that you get a cellular decomposition of the manifold using the stable and the unstable manifolds. Okay, so let me give you a picture that should help you. So maybe I can erase this part and give you an example. Okay, so I have the sphere again and an S here, and you see the idea is that these give a cellular decomposition of the manifold S2 or M in general. And so you can write it as a cellular complex, which means you can write it as a union of some subspaces of subsets of this manifold in a meaningful way that they attach nicely to give you the whole sphere. Okay, so this is the stable manifold at n. So what's the stable manifold? Okay, anyways, let me write down the complete thing and then we'll try and compute. Okay, so we have the stable manifold at n union the unstable manifold at n union the unstable manifold at S. Okay, so what do we have here? So we're looking at the stable manifold, and we're looking at downward trajectories. Remember, this is what they look like. I have green over here. This is what they look like, pointing downwards. Okay, so we're looking at the downward trajectories, and so which are the points that lie on these trajectories that go into n, that are moving towards n. So you'll have to flow along the opposite of downward trajectories, which is not allowed. So what would the stable manifold be? You can imagine that this is going to be empty. So we have nothing here. Okay, there are no points that go into. You have lots of points along the trajectories that go out along the downward flow lines, out of n, but never into n. Okay, and what about the stable manifold? So this stable manifold here, sorry, I wrote an S over here. So now I'm looking at the stable manifold, all points that lie on downward trajectories that are coming into S. Okay, so you see this is defined as a limit. Okay, we don't include the S over here. Okay, I chose not to write down this definition, but this is that they limit to P, all points that limit to P along flow lines. Okay, so this does not include S. But what do we know from point B? We know that S is of index 0. So this is R to the complementary dimension of the index of S, which is 2 minus 0, that's 2. So this is homeomorphic to R2. Okay, and because the index of S is 0 and n is equal to 2, that's the dimension of the sphere. And what do you have in the unstable manifold of n? Again, you have points that are leaving n. Okay, so it's the same as this thing over here. Okay, and what are the unstable? What's the unstable manifold at S? These are all the points that are leaving S, and since there are no points that leave S except for S itself, which just sits there, so all we have here is the only lonely point S. Okay, so that's the cellular decomposition of S2. using stable and unstable manifolds at critical points of S2 of this Morse function, which is given by the height function on S2. Okay, and this is consistent with the usual cellular decomposition of. So if I take this disk, and which is homeomorphic to R2, and I take this point and I attach along the boundary to this point, identify the boundary with this point, I've basically compactified R2 to S2. Okay, so you get S2. All right, so it's consistent with what we know about the cellular decomposition of S2 in general. Okay. All right. So in fact, there's a very nice theorem by the name of Reeb theorem, which says that you see, on a sphere, you can always find the Morse function with two critical points. That's the height function. Yeah, but it's like it says the opposite, which is if M admits Morse function with two critical points, so converse, then this M must be homeomorphic to the sphere. It's nice. Okay. So you see the power of the dynamics using functions or on a manifold, and flow lines and trajectories and so on. Okay. So all right, so let's come to these pictures, in fact the steps. So the first thing I want to quickly talk, so I'm insisting so much on Morse theory is because I will just formally say what the definitions are in the floor context, and we'll just follow the same kind of steps. It's the same kind of scheme of things, and we'll just generalize. Okay, so let's see. So the first thing we want to do is achieve transversality. That's step one. Remember, for what? For defining the differential. So F, this is the definition. F is called Morse-Smale, or it satisfies the Morse-Smale condition at P if, or let's say, sorry, I should say it satisfies the Morse-Smale condition, not at P, but for every critical point, for any PQ what do I want to say? The unstable manifold at P transversely intersects the stable manifold at Q. Okay. So I'm hoping that you're familiar with the transversal, what a transverse intersection is. So a transverse intersection is used to define something which is like the opposite of being tangent, in the sense that you have two, let's say, subspaces inside a bigger space. They intersect transversely if the tangent, their collective tangent spaces, they span the tangent space at where they intersect for the bigger space or the bigger manifold. Okay, so that's something, for instance, you cannot achieve with being intersecting in a tangential manner. Okay, so if you have one subspace that's tangent to the other, you cannot achieve the same. So for instance, I mean, if you look at this, you look at this line, the parabola, and this one, they're tangent at a point. That's not a transversal intersection. But if you look at this, the same line, and maybe like this, then you see that the tangent space here and the tangent space here is collectively two-dimensional, and it gives you a tangent space at this point in R2. It gives you tangent space to R2. We're looking at R2 at this point. Okay, you need a two-dimensional thing to span a tangent space at this point for R2. Okay, and the same goes for this intersection. This is transversal, this is not. Okay. And of course, if they do not intersect at all, then it's also vacuously true that they're transversally intersecting. Okay, so good news is that any Morse function can be approximated by a Morse male one. Okay, so there are some consequences which maybe I should mention. So of all of this discussion of stable manifolds and unstable manifolds and these space M and its quotient L, there are some consequences that I can quickly mention. So the first is the following. If your index of P is less than index of Q, then what does that mean? P is at a lower level and Q is at a higher level, and so you cannot have a trajectory going from P to Q. Okay, so this means that this needs to be empty. Okay, if you have the reverse inequality for P which is different from Q, then we know that the dimension of this, what this dimension is going to be. So this dimension is I of P, index of P minus index of Q. Okay. So in this case, this MPQ intersects transversely every level set. See this yellow one? There was a slice of M. Yeah. So you just got these 1 point representatives for each trajectory going from P to Q. So you have this. And you have a transversal intersection. You see all the flow lines, they intersect very nicely. So it's like not in a tangential manner, but like quite the opposite with that, with this level set. So this thing, yellow thing, is what I said is the level set at alpha. Okay. So they intersect for every alpha that's a regular value of f, okay, outside the critical points. It's between P and Q, or images of P and Q, and LPQ is, so you can take the quotient again by that action, and when you take the quotient by action of R is one dimensional, it reduces the dimension of this further by 1. So this is of dimension index of P minus index of Q, that's the dimension of M, minus 1. Okay, this is because you lose one dimension when you take the quotient. And now if index of P is equal to index of Q, that can happen. You have two critical points at the same index. So for instance, here you have two critical points at the same index. Then the flow lines are empty. Okay, and if finally if the index of P, let's say Q, is index of P plus 1, what does that mean? That they are of consecutive index. Okay, so you have an index for P, and then you have one jump, and that you get an intersection point, a critical point which is of index 1 higher. Okay, so they have a difference of 1 between. So there are two consecutive index critical points. Then what does that mean? Their difference, you know, is already 1. That's the dimension of M, and 1 less would be 0. That's the dimension of L. Okay, and since we want to count these trajectories, it makes sense to count their 1-point representatives. So when you look at these 1-point representatives, you want they form a manifold of dimension 0. You want it to be compact, so you can count them so that the count is finite. So we want this L to be compact. So the count is finite. Okay, so you can count. Okay, all right. So all right, I have the skewed torus, but I don't quite remember why I drew this. Okay, maybe I can come back to this later. So this is what we want. You want them to be compact. Okay, so that's the part where I probably missing something. Just give me a second. Okay, right. So basically this transversality, it ensures that this M is of the right dimension. Okay, so that's why you need transversality. Compactness ensures that you have a well-defined differential because you need to count these trajectories. Okay, so that's the compactness step. And then boundary just means that you have a boundary map. The differential set squares to 0. Okay, so that's checking that this is indeed a boundary map. Okay, which is required to define homology. Okay, so now I can say something about compactness, and then we define the differential. So compactness so this is achieved by enlarging the space L. So you just add limiting trajectories, okay, to the existing trajectories in L, and you compactify. Okay, so you expand the space L to, let me call it L bar. Okay, so the claim is that this L bar, which is the union of trajectories or one point representatives, so between P and Q, so this is L bar of PQ. Between P and Q you have intermediate critical points, so let's say P1, P1 and between P1 and P2 blah blah, and finally let's say PR or PR minus 1 and PR is Q. Okay, you end at Q. Now draw a picture in a moment. So these PI's, very important, are different from PJ's. Okay, for I different from J, so that you have intermediate critical points and you get these trajectories that you add to compactify. Okay, so now let's just draw the okay, so maybe I have them drawn over here already, so I can go to this picture to draw this again. So I have this picture already, and you see that, let me draw with a red, this flow line that goes from this critical point to this one. So it's what you call a broken trajectory. Okay, so it stops at this critical point for a bit and then moves down to the other one. Okay, and then you have the rest of them here between. Okay, and what you see is that these broken trajectories, so maybe I can use this part of the board so I can also show you the picture. So these broken trajectories through intermediate, those are the PI's in between P and Q, critical points. So these are the red ones in the picture, are the limits or the boundary points of the unbroken ones. Trajectory segments between non-consecutive critical points. Okay, so that's important. The ones that PI's and PJ's over here were, so these two are consecutive. P1 is the next critical point after P, and then P2 is the next one after P1. So they're consecutive, 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 and to begin with, you had a jump from P to Q of index more than 1, and in between you break them into these intermediate, and those are the limiting ones that you add. Okay, so right, and okay, what do I want to say? Sorry, I made a small mistake, which is small, not really small, but what I wanted to say here is that this, the claim is that this is compact, and while in just a minute. right. That's fine. So this is compact, and you just add these the broken trajectories. So you add, I should write to this, to L, these broken trajectories. Okay. Yeah. Okay. And so you get a compact manifold, and these trajectories, these occur in pairs. Okay. So that means that the count mod 2, because the complexes, you remember, were defined over R2, Z mod 2. So the count mod 2 is 0. Okay. So that tells us that, well, that indicates that we can finally define the differential, which is given by delta k from, let's say, Ck of f to Ck minus 1 of f. So from index k critical point to an index k minus 1 critical point. Okay. So this delta k of p is defined as the sum over all critical points of index 1 less. So q is a critical point of f, which is of index 1 less than the index of p, and you count them with the number of trajectories. So this is n, this number npq. Okay, so it's a weighted count. So you weight it by the number of trajectories, and this npq, the coefficient, is in Z mod 2, because everything is, these are also complexes are defined over Z mod 2, and it equals the count of trajectories in the compactification, I should say PQ mod 2. Okay. So which is 0 dimensional plus compact, this count is finite. Okay. Yeah, that's not what I wanted to say over here. So maybe let me make this correction, because that's part of the boundary thing. So sorry about adding this. So maybe you can strike this out, because I didn't want to say that there. So we've achieved compactness so that we're able to define the differential. Now we need to check that this is indeed a boundary, which means that it squares to 0. Okay. So for this to square to 0, maybe I can erase this side. So this delta k composed with k minus 1 composed with delta k is, sorry, did I write it the other direction? Yeah, but delta k minus 1 going over here, so it's delta k first, and then it's delta k minus 1. Yeah, that's fine. Okay, so this squares to 0, and the proof relies on showing the boundary of trajectories here between two, so it's not a consecutive index. This is, I'm looking at this map and then this map that goes to ck minus 2. This is a jump of 2 in the index, okay? So you go from here to here and then here. So you compose these differentials, you should get a 0 over here. So now you're looking at a critical point here, which is C, and a critical point here, which is D. Okay, so you're looking at Morse trajectories that go from C to D, and that's the manifold we compactified, the LCD we compactified. Okay, so the boundary of this thing is of the correct dimension. Okay, so what does that mean? So the dimension of this is the same as the dimension of L, and since the difference between the indexes C and D is 2, the dimension of L is 1 less, which is 1, and so is the dimension of the compactified L. Okay, and so this is of dimension 1, and it's compact. So we use the fact that if you have a compact one-dimensional manifold and its boundary is is either homeomorphic to the closed interval 0, 1 or the circle S1. Okay, so in this case the boundary is 2 points. Yeah, and in this case the boundary is empty. Okay, so you have a 0 mod 2 here, and you have a 2 mod 2, which is 0 mod 2 again. Okay, so the count gives you 0. Okay, so yeah, so you just write it down like this n from C to, let's say, something intermediate over here. Let's call that I don't know, E, C to E times n of E to D. Okay, and so collectively this number comes down to 0, and so that gives you that this differential squares to 0. Okay, so you see this compactness is absolutely unavoidable and essential in this, and otherwise you can't arrive to the conclusion you want. So I'm just going to give you quickly some examples finally, computing maybe these examples. So we already have seen the Morse homology for, so I mean, I don't really need to give you the definition of Morse homology. You have a complex which has a differential, and now this Morse complex, you take the homology of this Morse complex, you get the Morse homology. So that's already there, that's our definition. And so we can look at, we've already looked at S2, so I'm not going to repeat that. And I can look at now the, let's say, the skewed torus, but I haven't drawn the skewed torus, so maybe I can look at the deformed square, the sphere. Okay, so I'm looking at this X over here. So I'm looking at this deformed sphere. Okay, so this has, using the height function, it has 4 critical points. And now if you look at the Hessian and you look at the principal, the Gaussian curvature at each critical point of the function, the height function for this, you will realize that you have, well, you can also see them visually, that you have 2 local maximums, you have 1 saddle point, and you have a local minimum. Yeah. So the minimum is of index 0, the maximum are of index 2, and the saddle points are of index 1. So what you get is complex is 0, C0 of x, C1 of x, C2 of x. Okay, and this is isomorphic to 2 copies of Z mod 2 because, well, let me write it's equal to Z2 generated by, so index 0. Did I get this right? Yeah. Okay, so you have this, let me call this, I don't know, let me call this A, B, C, D, the critical points generated by D. This one over Z mod 2 is generated by B, and this one mod, sorry, am I have my arrows reversed. Apologies for this, this wasn't making sense. Okay, let me write this down again. So you have 0, that's D1, that's D0, and that's D2, okay, and there's nothing in index 3, so we have a 0 over here. And now this is Z mod 2 and generated by A and C, okay, all right, of index 2. All right, so I mean there's nothing, all you need these critical points for is, at least at the level of defining the graded module, is that you need the count at a certain index. So this is basically just a copy of Z mod 2, that's a copy of Z mod 2, and that's a copy of Z mod 2 twice, okay. Okay. So now you're going from right. So in going from right. So what is this? This is clearly 0. What's this map? It takes degree 1 to degree 0. Yeah. Sorry, index 1 to index 0. Okay, so this D is the differential is defined by what do I want to say? Just a minute. Okay, I need to go back to the definition. So that's the definition. Okay, so you're going 1 index down, and that's the number. Which is the count of trajectories, okay, and this has got to be 0 dimensional, okay. So now you have this 1 dimensional between 2 consecutive indices, 2 consecutive from B to D, you have trajectories between 2 consecutive, you have 0 dimensional L, 1 dimensional M, 0 dimensional L, and this is going to give you the trivial map. So this is just the trivial map, that's D1, and from B, from AC, so from index 2 to index 1, you have these trajectories that I can draw with the red here, okay, going down to B, and this is given by this matrix 1 1. Okay, so you just apply this matrix on the left, so you get here you have a vector in terms of A and C. So this is like this, you have 1 1 and a multiple of, I don't know, A, and a multiple of, I don't know, C, and you do it and you get something in terms of you get one entry, a 1 cross 1 thing, and that should fall over here in terms of P. Okay. So let's look at, so you forget about the reason I wanted you to identify them with just copies of Z mod 2 and just think in terms of these linear maps. Okay. So now what you have over here is the kernel of D0 is everything, Z mod 2, and here you again have the 0 map, so there's nothing in the image. So the kernel of D0 modulo image of D1, that's H0 of x, okay, and that's Z mod 2. H1 of x is the kernel of D1 modulo the image of D2. So the image of D2, the kernel of D1, first of all, it's just the trivial map, so it's got to be everything. So this is Z mod 2, okay, or one dimensional over Z mod 2. And so let me write it like this. So this is one dimensional. And what's the image of D2? You see the image, this is something two dimensional here going down to one dimensional. Okay, so in the kernel of D2 you have one dimension, so the rank of D2 has got to be 1. Okay, so the rank of D2 is, or the image is of one dimension, and so you get something that's trivial in H1, and H2 is kernel of D2 modulo image of D3, which is already trivial. So there is nothing in the image, and the kernel, we've already said, is Z mod 2. Okay, so what you get is nothing in degree 1, homological degree 1. You get one copy of Z mod 2 in 0 degree and one copy of Z mod 2 in the second degree, which is again consistent with the homology of the sphere. Okay, and that shouldn't be a surprise for us, because homology, whichever variant you take, is an invariant of your space. Okay, which means that if you deform the space in a nice continuous fashion, then the invariant remains the same. It remains, so that's the invariance property of homology, and the same goes for Morse homology. Okay, so that's not a surprise that the homology of the deformed sphere is the same as the homology of the sphere S2. Okay, so in the interest of time, I should stop here, and unfortunately I was unable to give more examples. So yeah, so it's been a long a lot of detail on Morse homology. Unfortunately, we didn't touch floor theory in this lecture, but I promise to do this tomorrow, and so we'll just recover and just mimic everything we've done today for Morse homology, and just try and set up floor theory using what we did in Morse homology today. Okay, and I'm just going to give you briefly an introduction to symplectic manifolds so that floor theory starts making sense. And yeah, hopefully this Morse homology has made some sense. And yeah, maybe if I think if I have time, maybe I can write up an example for tomorrow to give you another instance or another computation of Morse homology using the setup that we have. Okay, so that's all for today. Maybe I can ask if there are any questions that I'd be happy to take.